Today we're continuing the unification of physics. In the two videos before this one, we discussed parts of classical physics, Newtonian mechanics, Newton's theory of gravity. It was an action at a distance theory. The development of Maxwell's electromagnetic theory. He unified light, electricity, and magnetism into one field theory. His theory differed from Newtonian mechanics. Newton's theory of gravity was an action at a distance formulation. But because of the violation of Galilean relativity in Maxwell's electromagnetic theory, there was a conflict between Newtonian mechanics and Maxwell's theory. It was Einstein who resolved that conflict through his special theory of relativity. He did that by uniting space with time, but this fix was only valid in inertial reference frames, where two observers were moving at a constant velocity relative to one another. In the last video, we showed that classical physics was not up to the job of describing physics at the small scale. And so in this video, we're going to discuss non-relativistic quantum mechanics. We're trying to get here. We've gone some of the way on this side of the ledger. We need to discuss in future videos the development of general relativity, and we've gone some of the way on the quantum side of the ledger and explained how classical physics wasn't up to the job of describing physics at small scales, and we're eventually trying to get to the standard model. And if you remember, general relativity is logically incompatible with the standard model. We are trying to find a way of unifying the two and come up with a quantum theory of gravity so that our universe is described with one consistent theory rather than two inconsistent theories. And that's what we call the unification of physics. So let's get started with non-relativistic quantum mechanics. In the previous video, we looked at several situations where classical physics broke down. The Rayleigh-Jeans law didn't predict the correct emission and absorption of radiation by a body. Einstein showed that light could act like a particle. This directly contradicted Maxwell's wave theory of light. The Bohr model of the atom showed that the electron could only assume certain energy levels, certain orbits around a nucleus, and that was at odds with Rutherford's model. And then de Broglie's wave-particle duality, which said it was impossible to tell whether or not the electron was a wave or a particle until it interacted with a measuring device. And all these events and situations led to what would become known as non-relativistic quantum mechanics. This was the theory that was going to incorporate all laws over here into a theory. It was developed in the early 1920s by Edwin Schrödinger and Werner Heisenberg. The first thing that had to happen, there had to be something in quantum mechanics that described the quantum system prior to a measurement. And that something turned out to be the wave function. It's a little bit odd in that it doesn't have a physical significance under the most popular interpretation of quantum mechanics, the Copenhagen interpretation. All the information about the quantum system is contained in the wave function, but you can't get it out without taking a measurement. It doesn't provide real physical outcomes. It can only provide probabilities. The square of the wave function is associated with a probability. So, for example, we know that the electron, if it goes through here, it's got to go through one of these openings in order to show up on the screen. So there's a probability that it would go through one of the openings and a probability that it would go through the other opening. If you remember, there's a 50% chance it goes through this opening and a 50% chance it goes through that opening. That's where the probability of the wave function comes in. If psi squared is going to be a probability, all the values that the square of the wave function can take on has to add to 1. And so, for example, Here, the electron has to go through one of the other of the openings. There's 1/2 a chance or a 50% chance it goes through this opening, and a 50% chance it goes through the other opening, and that adds up to 1. And this is what this characteristic of the wave function shows. Now, the wave function is a function of position and time. It can be a function of position only. There is a wave function that's just dependent upon position in space. There is a wave function that depends on position in time. But whether it depends on time or not is unimportant in this description. It turns out that the outputs of the wave function are complex numbers. Now, some of you probably don't know what a complex number is and why is it a complex number. For example, if here's the wave function, it's a function of position. I'll just call position r, and time t. Sometimes t is not involved, but that's not important for this. And it produces an output, produces a complex number, something that looks like that. Both a and b are real numbers, but a complex number has a real part and it has an imaginary part. This is the real part, and this is the im part, the imaginary part. So it's really made up of two numbers rather than just one number. The wave function is said to be in superposition, kind of a controversial aspect of quantum mechanics, because we never see the wave function in superposition. When we take a measurement, the result is always a real number, a real value, and in fact, in this case, it's a probability. So why do we represent the wave function as a complex number? Well, you can kind of give it an idea that if the electron is a wave, it has to be in two places at once. In other words, it has to pass through both slits at the same time. Otherwise, it wouldn't have wave properties. And so this is a way of expressing that. This says that the electron can have two parts. Any quantum system is like that, but the electron can be in two places at once, in other words. So it has the ability to pass through these openings at the same time in order to produce a wave pattern, an interference pattern on the detector screen. The outputs of the wave function are complex numbers, but the square of the wave function is a probability. And so it has to actually be a positive real number. Now, how do we get a positive real number from that? Well, the way physicists take the square, so if we say the square of this is really equal to something like this, where this psi here is the complex conjugate, it's A plus IB multiplied by A minus IB. This is that part, and this is that part there. And then when you multiply those out, you get A squared, and you multiply here, you get minus IAB, and multiply here, you get plus IAB. And then you multiply here, you get b squared. And so these two sum to 0, and you get a squared plus b squared. Now notice something here, that a squared, no matter whether a is positive or negative, a squared is positive. So this is a positive number. It's greater than 0. And it's also a number that sits between 0 and 1. It's a probability. That's what this says. This characteristic here of the wave function just says that for every r and t that we input, for every position in time in the evolution of a wave function, we only have one output. It wouldn't make sense if we had, say, and these were not equal, if we had two outputs at the same time. You couldn't have a 50% chance of the electron going through this slit and a 30% chance. That wouldn't make any sense. That's what that just says. For every input, every r and t, there's one output. We don't get two, so it's a function in that sense. Now these two characteristics of the wave function are mathematical characteristics. But it is important to note that the wave function is three-dimensional. So it's a function of x, y, and z. Remember your coordinate systems here. This is z up here, probably an x along here and y along here. This wave function gets a value for every position, and if you want to add time in there, you can. It's not important for this discussion, but it's, we could put a t in there if we wanted to. We have this wave function. What do we do with it? Well, in Schrodinger's formulation of quantum mechanics, you take the wave function and you plug it into Schrodinger's equation. It looks like this. I'll explain to you what this represents in a minute, but you can see that it's a function that measures the energy of the quantum system. So this piece here represents the kinetic energy of the system. This piece here represents the potential energy, and if you add them together, you get the total energy, and that's represented by this piece here. So there has to be some way of representing or dealing with a quantum mechanical system after a measurement. The wave function describes the system before a measurement. What describes the system after a measurement? And the answer to that question is the quantum mechanical operator. This is the second postulate of quantum mechanics, and it deals with operators. You probably can't see this, so I'll read it to you. For every measurable property of a system, such as position, momentum, and energy, there exists a corresponding operator in quantum mechanics. An experiment in the laboratory to measure a value for such an observable is simulated in the theory by operating on the wave function of a system with the corresponding operator. So what does that tell you? This is called an eigenvalue equation. This O with a hat on it signifies an operator. It operates on the wave function, and it extracts information. When we take a measurement, then we will know something about the quantum system. And so it extracts information from the wave function. The information is packaged in this Greek letter. It's called an eigenvalue. The operator represents taking a measurement. Now, there's an operator for each measurement. For example, if you want to measure the momentum of a system, then there's an operator for that. You can see it over here. You probably can't see it. It's too small. But there's an operator for that. And if you want to measure position, there's an operator for that. And if you want to measure the energy of a system, there's an operator for that. So, for example, if I want to know the momentum, we might, in the x direction, we would operate, I'll call this, that's an operator, px, that's the momentum operator on the quantum system, and it would give us some, I'll just write this as k. And this would be the momentum, and it would tell me that at position r, the momentum was k. If I wanted to know the position, I would use a position operator. This is kind of odd, but I would operate on the function. It would give me r. It's kind of obvious, but that's the way it works. Oh, I should mention one thing, the idea of a commuting operator. What does that mean? We probably should put a little hat over that to say that a classical position goes over to a position operator in quantum mechanics. And we should probably put, this would be p hat x here. That concept of momentum in classical physics goes over to an operator in quantum mechanics. And so if we put little hats on these to indicate that they're operators. If you remember, in the last video, we talked about the Heisenberg uncertainty principle. And what that said was that it was not possible in quantum mechanics to measure the momentum and position at the same time. And this is what these commuting operators indicate. This is called a commutator with these brackets around it. We can define the commutator like this. X p minus px. That's how it's defined. If these are just numbers, for example, these are operators. But if they were just numbers, It would be pretty obvious that this commutator would be equal to 0. But if they're not just numbers, if they're operators, they don't necessarily commute. And that's the way in quantum mechanics that the Heisenberg uncertainty principle is utilized. In this case, we cannot measure momentum and position at the same time. This is not 0. Happens to be an imaginary number, but that doesn't matter. And it's not important for this discussion. And so equations in quantum mechanics that contain these operators, there are many equations that might, where these operators show up. If the commutators compute to 0, in other words, if the two operators commute, those terms where those commutators appear just vanish, and you pretty much get classical results, not all the time, but most of the time. But when they don't commute, then the equations that utilize these commutators in quantum mechanics don't vanish, and you get a very much different answer than you would in classical physics. And so this is a big difference between classical physics and quantum physics, because many of the equations in quantum physics contain these commutators, and if operators don't commute, then you get non-zero terms that don't show up in other equations. So what do non-commuting and commuting operators represent in quantum mechanics? Well, non-commuting operators, where the commutator is not equal to 0, represent measurements that cannot be known at the same time. And that's consistent with Heisenberg's uncertainty principle. If the commutators is equal to 0, then it tells you that the two operators, or the two measurements that you are interested in, can be measured at the same time. And so you can know those values at the same time. For example, if we replace x here with the energy, or with h, for example, h hat, that's the energy, and we'll talk about that in a minute, that would be equal to 0. And in that case, we could measure the energy and the momentum at the same time. Some operators commute and some don't. We talked a little bit about this h hat operator. It happens to be right over here. You probably can't see that. It's right there. So if we're measuring the total energy of the system, that's what that operator does in quantum mechanics. And if we looked really close here, let's just factor out on that side psi r out of this equation here. What do we get? We get with it, it'll be minus h squared over 2m. Then we have this little piece here plus the VR. I guess this is a capital VR here. We would put that in a bracket, and that would be R, and that would be equal to E, and I'm running out of room here, but R. What you'll notice here is that this piece in here looks exactly like that, or very close. This is one dimension, this is 3 dimensions, but that's not important for our discussion here. It just shows you that this piece, we can substitute h hat in for this piece, and if we do that, we just get h hat times the wave function is equal to E times the wave function again. Well, if you'll notice something here, that looks an awful lot like that. Schrodinger's equation is an eigenvalue equation. It represents a measurement. That's why we plug the wave function into it. The h hat is that piece, the wave function, and then E is the eigenvalue, and then the wave function again. This is this piece. And what that tells us is that we're operating on the wave function with an energy, a total energy operator, and it's going to give us the total energy at position R. Now, where the probability comes in, it's certain that if we measure the energy at position R, it will be E. We would have to calculate the probability that the system is at position R. And that's where the probability comes in. It doesn't come in here. It comes in with the wave function. If we measure energy at position R, it's going to give us a definite value. And that makes sense because we've taken a measurement. So that's quantum mechanical operators in a nutshell. I'd like to discuss a little bit more about the wave function of an atom. It's a little bit of a misnomer. This is not really the wave function of an atom. What it is a wave function that tells how the electrons are configured around an atom. It doesn't tell us anything about the nucleus of an atom. It just tells us how the electrons are configured around the nucleus of an atom. As I probably mentioned, the wave function is three-dimensional. The wave function is a function of x, y, and z. And sometimes t, but we're going to not pay any attention to t. At this point, we're just going to use the time-independent wave function for this exercise. Mathematicians like to write the wave function in terms of spherical coordinates. Instead of Euclidean coordinates x, y, and z, this would be z up here, and this would be x here, and this would be y here. Physicists like to write them in spherical coordinates. Spherical coordinates are shown over here. They're a function of r, which is just this vector here, phi, which is this angle here, and theta, which is this angle here. The reason they want to do that is because you can write x, y, and z in terms of r, phi, and theta. So r, it's just x squared, y squared, plus z squared. If we look at this equation down here, we can write that z is equal to r, but r is just the square root of this, so we'll write that in. So this would be x squared, y squared, plus z squared, cosine of theta over here. Then if I divide through by this, I get z divided by x squared plus y squared plus z squared. And that would be equal to cos theta. Then if I just take the arc cosine of both sides, theta would be equal to arc cosine of this, z divided by the square root of x squared plus y squared plus z squared. Why we do that is because we can write theta in terms of x, y, and z. We already have r, which is this, in terms of x, y, and z. And so let's look at this part, y divided by x. And then we would get r sine of theta times sine phi, and that would be divided by r sine theta. This would be cos phi here. You can see that these cancel. This is just the tangent. We can write this phi as the arctangent of y over x. Whoops, y over x. And so why do you want to do that? We want to do that because instead of a three-dimensional function, we can write three one-dimensional functions, and they're a lot easier to deal with. What do they mean? I mean, this one can be, goes down to here, this one goes to here, and this one goes to here. So what do they represent? Well, you might guess, since this is a function of r, it predicts the distance from the nucleus that the electrons are circling, or the different energy levels. Now, Schrödinger's equation agrees with Bohr's equation for the hydrogen atom, which validated it to some extent, but it also predicts the correct energy levels for the more complex atoms, which Bohr's model couldn't do. N goes from 1, 2, 3, and so on. Now the next wave function, which was this one, called the orbital quantum number, the L here, can be 0, 1, 2, or 3. If you remember, L is equal to PR from the previous video, which is equal to N times H bar. And if we assign H bar equal to 1, then L is just equal to some integer multiple of H bar. And so L is quantized. And what it represents is the shape of the orbit They're called subshells. If the angular momentum is 0, its subshell is S, and it has the shape of a sphere. In quantum mechanics, it's the probability that the electron is somewhere on a sphere. If the angular momentum is 1, this is the P shell. It's a dumbbell-looking thing here. The probability that the electron is in this shell is given the L is equal to 1. And so on. This is the D shell, and this is the F shell, and it's just the shape of the orbit. Now, what does this quantum number represent? Well, it represents the orientation of the orbit. In this case, it's showing the orientations for the orbits of the dumbbell shell. It could be oriented along the x-axis, or oriented along the y-axis, or oriented along the z-axis. It turns out that m sub L can be equal to minus L up through plus L. And so it's quantized. And what this means is if we submerge an atom into an electric field, that electric field will orient the shells in a certain way. And this is just how the dumbbell shell is oriented in various combinations. This is just one of examples for each of the orientations. That's basically the wave function of the atom. Again, it's kind of a misnomer because it's not really the wave function of the atom, because it doesn't tell us anything about the nucleus of the atom. It only tells us about how the electrons are configured around the atom. But as far as being able to describe the way electrons moved around the nucleus of an atom, Schrödinger's approach was not quite up to the job. One of the things that revealed this was something called the anomalous Zeeman effect. It showed that orbits of electrons had more orientations than what the Schrödinger approach predicted. There was also something called the fine structure, where the energy levels were slightly different than what Schrödinger's approach predicted. It was fairly clear that something else was going on here, and that something else was called electron spin. It's a quantum mechanical effect. We're not going to get too much into exactly what it is, but it's sort of analogous to a top spinning around its axis, or the Earth spinning around its axis. What Wolfgang Pauli recognized was that the transitions into different states of the electron, he noticed that if the first three numbers, and we know what these numbers are, this is the energy levels, the shape of the orbit, and the orientation of the orbit. He recognized that in these transitions that this spin number or final number could not add up to 1 or minus 1. He assigned what he called a spin-up electron as having plus 1/2 spin, and he defined a spin-down electron as having a minus 1/2 spin. If you add 1/2 to 1/2, you get 1. Minus 1/2 to minus 1/2, you get minus 1. And he recognized that in any quantum state of the electron around the nucleus, if these three numbers were the same, this number could be spin up or spin down, but there could not be two electrons that were both spin up or two electrons that were both spin down. And that became known as the Pauli exclusion principle. So he sort of invented the idea of a quantum state. Quantum state of an electron was defined by these four numbers. So we had to have an additional wave function, we call it psi sub s, that was related to the spin of an electron. Remember, the other wave functions were the ones for energy levels, one for one for the shape of the orbit, and one for orientation. And then we have to add this fourth one to completely describe how electrons move around the nucleus of an atom. And what that allowed physicists to do is to develop the periodic table of the elements. If you're old enough, you might have seen this in your science classes or chemistry classes if you took chemistry in high school or college. These numbers were used as a way to build this table. And I'll show you how that was done. If you remember, the energy levels can be N can be 1, 2, 3, and so on. L, this number here, which was the angular momentum, it came in discrete units, and that could be from 0 to N minus 1. and the magnetic moment number, or the orientation number, took on values, discrete values between minus L and L, and the spin number, ms, it could be up or down. Those were the only two possibilities. So let's see how they built this chart. So suppose then that n is equal to 1. Therefore, L, or the angular momentum number, would be n minus 1, which is 0. And so m sub L would be equal to 0. But ms, the spin number, could be up or down. Electrons in the first orbit would be either up or down. It can only be 2 electrons at most. If there were 2 electrons in that orbit, one had to be spin up and the other had to be spin down. So this accounted for the hydrogen and helium atoms only. Now let's look at when n is equal to 2. Therefore, L would be equal to 1 from this formula, n minus 1 is 1. And then m sub L is equal to minus 1, 0, and plus 1. And so each of these could be spin up or spin down. So we would have, this could be up, this down, and so on for this one. So if we counted here, up or down, up, 1, 2, 3, 4, 5, 6, and then the second energy level, remember that this would be n equal 1, and that would be in the first energy level around the nucleus. That would be the second energy level. So there could be 6 electrons in the second energy level. What about n is equal to 3? So if n is equal, n is equal to 3, then L would be equal to 2. And then m sub L, using this formula here, would be equal to minus 2, minus 1, 0, 1, and 2. Those are the possible orientations. They're quantized, and each of those could be spin up or spin down. Spin down, spin up, spin down, spin up, spin down, spin up, spin down, spin up. So if we count those, well, there were 5 here, we have to double that. That would be equal to 10. So in the third energy level, there could be 10 electrons. To describe each of these elements in the periodic table, scientists used, or physicists used, scientist, E, that's an E, not, better write that better. This was the energy level. So this would be 1, 2, or 3. This was the subshell, or shape of the orbit, and this is how many electrons in that subshell. And so if we look here, here's an example. Notice that this is an example for a sodium atom. It tells us that in the first energy level, there are 2 electrons. One would be spin up and one would be spin down. In the second orbit, or the second energy level, there were 2 electrons in the S configuration. And in the third energy level, there were 6 electrons in the P configuration and 1 electron in the S configuration. And that defined the sodium atom. So each element in the periodic table has a unique code, looks like this. This happens to be the one for the sodium atom, but each atom in the table is described by the way the electrons are configured around the nucleus of an atom. Now this idea of spin became very important. We'll talk about relativistic quantum mechanics in a later video, but it was responsible for being able to distinguish the matter particles and the force-carrying particles. Matter particles, like the electron, were spin 1/2 particles. They were called fermions. And the force-carrying particles, they were called bosons, had integer spin. And that was a way of classifying the 2 major types of particles that appear in nature. Both these types of particles made it into the standard model of particle physics. And how that came about, we'll talk about in a future video. And what we did in this video is we added or had a fire hose discussion about non-relativistic quantum mechanics. And that was the first of the quantum theories. There were others that followed, and we'll have to talk about those. On this side of the ledger, we've talked about Newtonian mechanics. It led to a theory of gravity. It was an action at a distance formulation. How Maxwell unified optics, electricity, and magnetism into a theory of electromagnetism. It was a field theory which was different than an action at a distance theory that Newton had developed. But there was a conflict between Maxwell's theory and Newtonian mechanics in that Galilean relativity was violated by Maxwell's theory, and it was at the foundation of Newtonian mechanics, and the fix to that was given by Einstein in his special theory of relativity that unified space with time. It only applied to observers moving at a constant velocity relative to one another. And so we've gone quite a bit of the way in classical physics. We just have the general theory of relativity to discuss, and we'll do that in the next video. We have quite a bit more to go here. We have to talk about relativistic quantum mechanics and then quantum field theory. This is where we're trying to get to. In the next video, we will discuss general relativity. In that video, we'll finish this side of the ledger. We will also discuss relativistic quantum mechanics in the next video, and that'll get us closer, but not quite where we need to be to reach the standard model particle physics. Again, we remember that general relativity and the standard model are logically incompatible, so we would like to unify these two theories into one consistent theory that describes our universe, and that's what we call the unification of physics. So until next time, please tune in.